Hi everybody, welcome to another installment of SUPA Chemistry. I'm sure everyone's excited for another live action video. Okay, so today what we're going to do is I want to start by kind of recapping some of the SPDF orbital stuff that we were dealing with last class, and then we're going to continue on and talk about electron configurations of ions, and then we're going to get into what are called quantum numbers. So the very first thing I want to talk a little bit about those SPDF orbitals again. So if we start in my first principal energy level, okay, so if this is the first PEL, my first principal energy level only has one sublevel, and it is an S sublevel. Okay, and if you remember, the S is only a sphere. It's an area of space where we find electrons. Okay. Now the S sublevel only has one area of space. Okay, it has one area of space where we find electrons, and it will hold 2 electrons. Right? Now, if you remember back to your high school class, okay, hydrogen and helium, okay, hydrogen and helium only want, well, actually more than that, hydrogen, helium, lithium, beryllium, and boron, and sometimes, they only want 2 electrons. They only want 2 electrons. And the reason being is they're going to fill that 2s orbital. So they get an electron configuration of 2s2, which is a noble gas configuration. Noble gas configuration, which is what atoms like. They want this noble gas configuration. Okay, so once this orbital is full, once that 1s is full with their 2 electrons, it's very stable. Now, my second principal energy level, PEL2, it has 2 sublevels. It has an S and it has a P. Now the P sublevel has 3 orbitals. Okay, so this has 3 orbitals. So it will hold 6 electrons. This guy right here, that S, will only hold 2 electrons. So my second principal energy level total can hold 8 electrons. Now if we look at neon, neon has 10 electrons, and its electron configuration would be, 1s2, 2s2, 2p6. Here are my 8 what are called valence electrons. These are the core electrons. So my inner ones would be my core ones. The ones in the outer PEL are my valence electrons. Now, again, this is a noble gas configuration. It's very, very, very stable. Okay, now, so in my my second PEL, this would be my 2s. It would be a little bit further out than my 1s. And if you remember, the p orbitals, okay, they look kind of like dumbbells. So this would be one of them. This orientation would be another one. And then finally straight up and down would be my third. And each one of those orbitals holds 2 electrons. If we look at my third principal energy level, it has an S, a P, and a D. Now the S can hold 2, because it only has one area of space. The P has 3 areas of space, so it will hold 6 electrons. The D has 5 areas of space, so it can hold 10 electrons. So the third principal energy level can hold a total of 18 electrons. Now, if we look at argon, argon has 18 electrons. It's a noble gas, so it's one of those configurations that electrons want. So it would be 1s2, 2s2, 2p6. We got 6, 7, 8, 9, 10 so far. 3s2, 3p6. Okay. We have these 8 valence electrons. Very stable. Okay, that's what elements want, these full s and p orbitals. It's what makes them stable. These then are my core electrons. Okay, those would be my core electrons. Now, again, let's look through shapes again. This would be my 3s. Okay, it would hold 2 electrons. This would be my 3p's. Okay, this would be one of them. This would be one of them, and that would be one of them. And then remember, the D's are that 4-leaf clover shape. Okay, so they look like this. Can you see that? Okay, so most of them look like that at different angles, and this is the one that has that weird one, right? So it has that weird d orbital with this thing. Okay, let's see if I can do this. Okay, it looks something like that. Okay, with that ring. So there are 5 areas of space where we can find electrons. Okay. And then we could go into the SBDFs, and we just keep going. All right. Now, there's something I want to kind of show you that with the diagonal rule, and I don't know if you're using the diagonal rule, but okay. So I went this way across, where I went 1s, 2s, 2p, 3s, 3p, 3d, and made it this way. You could also go the other way. You can, let's see if I can even do it. Okay. Some people go up and down instead, and they do 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and instead of going, you can do it this way too. All right, and this is what some of the other videos show. So you can go 1s, 2s, 2p3s, 3p4s, and this is just giving your off-ball filling things again, all right? The order of filling. It doesn't matter which way you do the diagonal roll. And you don't even really have to do the diagonal roll as long as you know the order of those electrons. Okay? All right. So that's just kind of a little bit of a summary. And we're going to go into ions now. So this is the electron configuration of ions. So atoms want a noble gas configuration. Okay, so atoms want that noble gas configuration. They're going to gain or lose electrons to get that configuration. So nitrogen, let's start there. Nitrogen has 7 electrons. So its configuration would be 1s2, 2s2, 2p3. Its orbital notation would be this: 1s, 2s, 2px, 2py, 2pz. We would have an up, down. We would have an up, down, up, up, up. So it wants a noble gas configuration, okay? And nitrogen will do different things, but usually nitrogen becomes a -3 when it becomes an ion, which is telling us it's gaining 3 electrons. Well, why does it want to become -3? Well, it wants the valence electrons to be 8. Okay, so it's going to either gain or lose those electrons to get those 8 electrons. So in this case, it's going to gain 3 electrons. One of them's, let's use this one. One will go there, one will go there, and one will go there. So the electron configuration of n-3 would be 1s2, 2s2, 2p6. And this would be the electron configuration of neon. So these atoms are going to become ions, and the way they become ions is to get this noble gas configuration. Okay. Now, let's look at magnesium. Magnesium has 12 electrons. Okay, so if we write its electron configuration, it would be 1s2, 2s2, 2p6, that's 6, 7, 8, 9, 10, 3s2. Orbital notation. Here's my 1s, my 2s, my 3s. This is my 2px, 2py, 2pz. This would be my 3px, 3py, 3pz. This does have d's, but we're not going to need them. Right, so in this case, we would have an up and a down. We would have an up and a down. Just so you know, we could go down, 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 up, up, up. All right, because remember, we're really just talking about spin here, okay? And we want to make sure that we understand that they have opposite spin. So you could go, it doesn't really matter, you could go down, 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 up, up, up. That's fine, but okay. Traditionally we always do up first. Then we have up and down. Okay. Now, magnesium wants a noble gas configuration. So to get there, we could add all these 6 electrons to get to be like argon. Or it could just lose these 2 electrons and drop down and be like neon. So if we look at the periodic table, okay, so here's my magnesium. It would have to gain 1, 2, 3, 4, 5, 6 electrons in the p's to get to be like argon. Or it could just lose this one and drop back, so we could lose this 3s and drop back to be neon. Much easier to lose 2 than to gain 6. So these 2 electrons right here are lost. It becomes Mg plus 2 with an electron configuration of 1s2, 2s2, 2p6, which again is neon. Now, if 2 ions or an ion and an atom have the same number of electrons and the same electron configuration, They are what's called isoelectric. They're isoelectric. So if we look at these guys up here, an Mg+2 ion has an electron configuration of 1s2, 2s2, 2p6. A nitrogen -3 ion has the same exact electron configuration. So N-3 is isoelectric with Mg+2 and an atom of neon. They would all be isoelectric to each other. So when we're forming these ions, okay, they're either going to gain electrons or lose electrons to be like the noble gases. Okay. Now, the transition elements are a little bit different. Okay, so when we're talking about transition elements, we're again talking about, this is that D group. Okay, so we're talking about filling D orbitals. And they do something a little bit different. Okay, they do something a little bit different. So let's go ahead and talk about transition metal ions. Now, okay, so these are all metals, okay, and the metals tend to lose electrons and form positive ions. So these guys are all going to lose electrons. Okay, you're not going to have any negative ions in here. So when the transition metals form cations, the outer s orbital electrons are lost first, followed by electrons in the d orbitals. Okay, so let's look at, let's start with manganese. So manganese, there it is right here. Okay, if we were to write its electron configuration, it would be argon. Okay, argon. Remember, this is just shorthand. And then we would have 4s2, and then 3d5. 1, 2, 3, 4, 5. Now remember, a half-filled d orbital is very stable. Okay, half-filled d orbitals are very stable. Okay, so what happens in manganese is it likes to form a +2 ion. And the reason it does that is it will lose these 2 electrons. Okay. And it will become an Mn+2 ion, and its electron configuration would be argon 3d5. Okay, so it loses these 2 before it loses these out here in the d orbital because this is so stable. Now remember, these orbitals, the 4s and the 3d orbitals, they're really close in energy levels. Okay, so the amount of energy that they have, it's not exactly the same, but they're pretty close. All right, so in the transition elements, they tend to lose these s orbitals, outer s orbitals, before they start losing them out of the d. So let's look at nickel. So nickel has an electron configuration of Ar 4s2 3d8. Now, nickel also likes to form a +2. Matter of fact, almost all of these transition elements like to form +2 ions. And the reason that they do that is they lose these 2 electrons before they lose any of the Ds. So argons, when nickel becomes an ion, it's going to lose these 2 electrons before it loses any out of the d orbitals. So its electron configuration is Ar, 4s2. Nope, I lied. Those get lost. 3d8. Okay, so it has lost those 2 electrons in the 4s orbital. Now, let's look at, what should we look at next? Let's look at iron. So iron has an electron configuration that's right here next to, it's right next to our manganese. So it has an electron configuration of Ar, 4s2, 3d6. Now, iron tends to make 2 different oxidation states. It will become Fe plus 2, but it will also become Fe plus 3. And let's see if we can figure out why it does that. Well, we know why it likes to form the plus 2, because it's going to lose these first. Okay, it's going to lose these s orbital electrons in the 4th PEL first, and we will get Ar 3d6. And iron does that a lot. But it also forms Fe plus 3. Why does it want to form Fe plus 3? Well, when it loses that 3rd electron, where does it come from? Well, it comes from this d orbital. And we end up with Ar 3d5. Why does it like this? Why does it want to do that? Well, if it loses that 1 more d orbital, it gives us a half-filled d, which remember is very stable. So iron is one of those elements that will form both of them, and that's why it likes to form plus 2s and plus 3s. Good. All right. Let's look at copper. So copper is argon, four S1, 3D 10. Okay. Remember, this is one of those exceptions. Now, copper, it likes to form Cu plus 1 ions. It's one of the transition elements that likes to form Cu plus 1 ions. Why? Why doesn't it want to be plus 2? Well, remember, it's a transition element. It is going to lose the 4s first. In this case, because of this exception of the Aufbau rules where we fill the d orbitals, okay, it's only got 1 s orbital to lose. So its configuration goes Ar 3d10. And it's lost the 1 4s electron. Right? So you have to kind of look at the original configuration, right, to figure out what's going to happen here. Okay, what's going to happen? Chromium. So if we look at chromium, it's another one of those exceptions. It's Ar 4s1 3d5. If you look at this, chromium is going to go +1 because it's going to lose this one electron. Okay, so that's another one of those exceptions. So you can kind of look at the electron configurations and you just got to figure out, hey, how many electrons? Now, for most of these, you have 2 electrons in that outer s orbital. So that's why most of the transition elements form oxidation states of +2. Okay, and that's where those oxidation numbers are coming from. We'll talk more about that as we go. All right. You'll be doing some practice and homework with these. The next thing we're going to talk about are what are called quantum numbers. There are 4 quantum numbers. And the quantum numbers identify the last electron in an electron configuration. It identifies the last electron in an electron configuration. So we're going to be looking at SPDF orbitals and PELs. We're going to use those to come up with these 4 quantum numbers. The first quantum number identifies the principal energy level. The first quantum number, remember there are 4 of them, so the first one is going to identify our principal energy level. This is often called the principal quantum number. And I've already told you that the principal energy level is denoted N. And it's really giving us the size of the sublevels. Okay, that's really, because if we're in the first principal energy level, it's small. Okay, and as we move out in principal energy levels, they get bigger and the sublevels get bigger and bigger and bigger and bigger. All right, now, so if I say I'm in n equals 1, okay, so if 1 is my first quantum number, all that's telling me it's the first PEL. It's the first PEL. If the first quantum number is n equals 3, we're talking about the third PEL. Now, the larger the n value, that tells us that we're further from the nucleus. It's a larger sublevel. The larger the sublevel. And remember, the more energy it has. And we're talking about where the electrons are. Okay, so the larger the n value, the more energy it has, the larger the sublevels are in reality, and the further they are from the nucleus. let's talk about our second quantum number. And this is the sublevel. The sublevel is our second quantum number. Okay, and the second quantum number is called the angular momentum quantum number. The angular momentum quantum number. It gives us the shape of the orbital. That's what it's giving us. Okay, so the second quantum number is giving us the shape of the orbital, and it's denoted L. And it's a lowercase cursive L. So L is a non-negative integer between 0 and n, remember that's my principal energy level, minus 1. Okay? So these are just numbers between 0 and n minus 1. And what this is